Now I'm going to discuss on the dot product. Okay, so the dot product, the name is also known as scalar product or inner product. Okay, so the result of this mathematical operation between the two vectors will be a scalar. So that's why the dot product is also known as a scalar product. Okay, so for any two vectors, so for example vector n a and b, a dot b, the dot product is equal to this equation over here. So you have to use the displacement in each of the direction x, y and z for both vector a and also vector b. Okay, so here I have summarized the properties of the dot product, which consists of four equations over here. However, I'm not going to discuss in detail all of this equation over here because I believe you have already been introduced to this equation in your math class. Okay, so instead for this course, I'm just going to focus on this one equation in the red box over here. Okay, which is a dot b is equal to magnitude a multiplied by magnitude of p and cos theta. So here cos theta is defined as the angle between the two vectors a and b over here. Okay, so you can also rearrange the equation and from there we can find the angle between vector a and b. So here you're going to use the dot product itself and also the magnitude of the two vectors. Okay, so now going on with the physical meaning of the dot product. So in dot product, whenever the two vectors, for example here vector A and B, are parallel to each other, it will be producing the maximum impact. Okay, so the scalar product for two parallel vector will give you the maximum magnitude. So I will have an example using a boat sailing along a river. So here, still with the definition, the dot product give the effective value, which is a scalar of two different vector. Okay, so again, we are going to use this equation over here. Okay, so here I have the boat and then the river. Okay, so now let's say that the river is flowing in this direction. Okay, so this will be our first vector and let's put this as vector a. Okay, as our second vector, that will be the movement of this boat here, and the boat is moving in this direction. Okay, so let's put this as vector b. Okay, so here the dot product between vector a and b will be, okay, the between the flow of the river will be a dot b, and we have the above equation, the magnitude of the vector a, which is the velocity of the moving water, and then second one will be the velocity of the boat, and then we have here cos theta. So this theta over here will be the angle between a and b. Okay, so these two should be a vector. Okay, so now we have the vector a here, vector b here, so I'm going to redraw that. Okay, so vector a is in this direction. This is b. B is in this direction, and then vector a is also in the same direction. Okay, so now the angle between these two vector a and b will be equal to okay, cos, not cos, okay, cannot do, okay, not cos, theta will be, which is the angle between the two vectors, will be 0 because it is parallel to each other. So here we have this equation as cos 0 degree. Okay, so this eventually will give us magnitude of A multiply with magnitude B multiply with cos 0, which is equal to 1. So finally this is only equal to A B. Okay, okay, so here we have the multiplier, like over here is equal to 1, so the velocity of the movement of the boat with the river flow will be the maximum value. Okay, so here we will achieve the maximum velocity of the boat. Okay, so now we'll take the same example, but this time we will let the uh, boat to be in this direction. Okay, so just like just now we have the river flowing in this direction with certain velocity, so that will be our first vector, vector A, and then this time the boat will be in this direction. Okay, so now B is in this direction, and then A is here. Okay, so the angle between those two will be this angle over here, which is equal to 180 degree. So we substitute to this equation over here, so we'll end up with A and then magnitude of B and then cos 180, which is equal to negative 1. So here you will have negative A B. Okay, so here instead of the velocity increasing like what we saw just now in this example over here, in this case uh, the two vectors is opposite to each other, and here the velocity of the movement of this boat over here will be decreasing, so we can show that using the value or the product from the dot product of the two vectors. So in this case the movement of the river flowing and also the movement of the boat. Okay, okay, so here in the previous example both of them are, the vectors are parallel to each other, so here you will have the maximum from the example the maximum effective value. Okay, and in this case you will have the minimum effective value. Okay, so it is totally opposite to each other, the vector A and B, so you will get the least number of the effective value. Okay, so the equation of the dot product, we can use it in one more application. Apart from the from like the previous example, it will give you the effective value. So the equation of the dot product also will give you the vector projection. Okay, so the vector projection is given by this equation over here, which we uh, uh, get it from by rearranging the equation of the dot product, this one over here, and it is equal to A dot B over the magnitude of B. Okay, so this A cos theta over here is equal to the component of A, vector A along the vector B. So this is equal to the projection of vector A along the direction of the vector B. Okay, so I'm going to show you some figures to explain to you on the term projection over here. Okay, so let's say I have vector A and also vector B. So we have two vector over here, and I put a lamp on top of the vector. Okay, so this even though I put the lamp over here, there will be no shadow. Okay, because A is right is 90 degrees to vector B. Okay, so we'll see another example. This time we have vector B, the same vector B, but vector A is slightly angled like this. Okay, and then I'll put the same light bulb to it. So due to um, light bulb, the lights from the light bulb, you can see along this line there will be a shadow. Okay, okay, so the length of this shadow on vector B right here is known as the projection of vector A, sorry. Okay, so here due to the light over here you can see a shadow. So this shadow is known as the projection of vector A on along the length of vector B. So this equation over here will give you this length over here. Okay, okay, so you can also use the dot product, the equation of the dot product to find the vector projection.